Next, we will discuss the workflow to develop an LH40 preparative method. The general workflow of the scale-up of analytical to preparative methods is the same, but the additional step of purity checks is included when using the LH40. Firstly, we would develop an analytical LC method, scale it up to become a preparative LC method, optimize the LC method, and then develop the fraction collection method. After all that, we would collect fractions to re-inject for purity checks. Functions that assist in this workflow are 1. The fractionation simulation to quickly produce a fractionation method. 2. The preparative parameter autogeneration to further accelerate the creation of a preparative method. 3. The preparative parameter improvement to enhance the preparative method. 4. The sample rescue in case of error to save precious samples. And 5. The parameter adjustment in the sequence window to showcase all settings for complete control of the method. When developing the fractionation method, the simulation function will assist in auto-generating the method. The auto-generated method can then be fine-tuned to suit the chemist's purity needs. It can be adjusted through the different parameters available in the lab solution software. Additionally, Shimatsu's noise skipping algorithm will prevent any noise from being detected that can waste fraction tubes and vials. This algorithm can be adjusted through the peak sensitivity setting. Such an algorithm greatly saves chemists time. As chemists worldwide know, we cannot afford to lose precious samples. The sample rescue function will be a lifesaver for when a chemist experiences a possible fractionation mistake. With such a function, a chemist can be free from any worries about system errors. Preparative LC is designed for purification and collection of target analytes, employing larger injection volumes, higher flow rates, and fraction collectors. Controlling the sample solvent's elution strength is vital for achieving sharp, well-resolved peaks. A strong elution power can be problematic, particularly with large injection volumes, so optimizing sample solvent composition is key to maintaining chromatographic performance. Another item to take note is the column temperature effect. It is important to take note of the column temperature because of its impact on peak quality. This tends to happen when either there is a large temperature difference between the column oven and the mobile phase, a column with a large internal diameter is used, or the flow rate of the mobile phase is high. When there's a difference in temperature between the mobile phase entering the column and the column's oven temperature, a gradient can form. This gradient can affect the consistency of analyte interactions with the stationary phase. Moving on, we will look into LH40 features and operations. LH40, also known as the liquid handler, is a unit that acts as both the autosampler and the fraction collector. This gives it the ability to perform complex instructions that the FRC40 and FRC108 lack, such as purity checks. It also holds a proprietary injection method that minimizes carryover to minuscule amounts that will greatly suppress contamination. The full feature set of the LH40 is shown here. This includes various features like automatic generation of fraction collection methods, a sample rescue function, prevention of fraction overflow, capability of up to 4 detector signal input channels, and extensive functionality for inhibiting contamination. Most notably, the liquid handler's strength in its speed and efficiency through all these features are its advantage over the other fraction. As stated in previous parts, the LH40 can perform purity checks. This allows for increased throughput and reduced workload as the purity check can be done without changing the fraction recovery container. The diagram above shows the purity comparison of the individual components, shown as various colors, to its total sample, shown as black. Overall, the LH40 is the ultimate option to suit all the needs of a chemist in their preparative work.
Managing and distributing this large compound collection involves many tasks, such as storing, keeping, plate sealing, peeling, and liquid transfer. So, a highly integrated automated system was designed and implemented to satisfy our requirements for throughput, flexibility, and reliability while performing all these tasks. The automated system consists of 12 instruments. At its core is the Hamilton Verso M2 compound management system, a minus 20-degree storage system that's 3.8 by 2.2 meters in size, integrated with two Hamilton liquid handlers, a microlab star and a microlab starlet. The system has a total of 3 cables to handle all our working labware. There is also a centrifuge, a plate holder, an eco-acoustic liquid handler, a plate sealer and plate seal remover, and a rack reader.
We have implemented 10 different methods in the automated system. Let's focus on the 3 main methods used to prepare copies of the compounds collection for partner sites: compounds dissolution and aliquoting, compounds loading and unloading from minus 20 degrees storage, and compounds reformatting from 96 tube racks to 394 well plates. The EU Open Screen compounds collection comes from 2 main resources: academic research groups and commercial vendors. The commercial compounds arrive with dissolved in DMSO at 10 millimolar concentration in 96 tube racks. The academic compounds come as powder in 24 tube racks. First, the academic compounds need to be dissolved and aliquoted. For that, a CSV file with all necessary information for creating 10 millimolar DMSO solution is input into the Venus software, which controls the system. The 24 tube racks are then manually loaded into the Starlet and Lab Elite system, which scans barcodes, removes tube caps, and dispenses the correct amount of DMSO into each tube. After recapping, the racks are shaken and incubated on the Hamilton heater shakers for an hour to ensure proper dissolution. Then, the tubes are decapped again, and 1 milliliter of the 10 millimolar DMSO solution is transferred into 2 identical 96 tube racks. The 24 tube racks are automatically recapped with the Lab Elite, and the 96 tube racks are manually recapped and stored at minus 20 degrees in the automated Verso store. Finally, a CSV output file containing the sample's information is generated after the process.
So when partner sites request compounds, the unloading and reformatting process is initiated. The unloading starts by supplying the system PC with a CSV file containing the barcodes of the requested tubes. The information goes to the Verso software, which picks the requested tubes, sorts them into racks, and places them on the handoff slide for the H-Motion robotic arm to transport to the plate hotel. To initiate the reformatting method, a CSV file edited by the NIME software is supplied to the system PC to relay all the information about the location, volume, and identity of the samples. During reformatting, the plate hotel unloads the empty target plates, which are transported to the microlab star deck via the H-Motion. The 96 multi-pro pad then transferred the compounds from the tubes to the 384 well plates according to the instructions. After the transfer, the tubes are recapped and returned to the plate hotel. This process is repeated for up to 4 racks to fill the 384 well target plates. Once all plates are filled, they are sealed and returned to the plate hotel. Finally, the tube racks are automatically transported to the Verso, and all the information are updated in the Verso database.
The benefits of the system have been significant. Within 1.5 years, we have sent over 1.5 million compound aliquots to partner sites, consisting of about 300 plates per compound collection copy. Without this highly integrated automated system, it would have never been achievable. We are very pleased with the flexibility of our integrated automated system, the quality of the Hamilton instruments, and the support of the Hamilton team. We continue developing new methods to automate more tasks, and we envision adding more instruments to the current setup.
When we first met EU OpenScreen, we understood that they were searching for a solution that could combine several complex methods requiring the integration of multiple devices and could be operated via a main interface. Over the years, Hamilton has accumulated extensive experience integrating third-party devices and developing complex automated workflows. We have a dedicated team handling these types of projects, including the design and manufacturing of special adapters and modules to allow for the physical integration of devices. In the case of EU OpenScreen, the largest and most complex instruments controlling the complete process are Hamilton robotic systems that are inherently able to be integrated with each other. Our liquid handlers are physically integrated into our storage systems via dedicated input-output modules, and the software communicates seamlessly. For the integration of all the other third-party instruments, we use custom drivers that allow Venus to control them all via a central hub. From standardized to highly complex integrated automation workflows, Hamilton provides the perfect solution.